Hi everyone. Now that we've seen and are a little bit more familiar with the four main carboxylic acid derivatives, in this video I want to try to explain why we see these reactivity trends. Why is the acid chloride more reactive than the anhydride, which is more reactive than the ester, which is more reactive than the amide? Okay. So here I have listed in order the reactivity of our four carboxylic acid derivatives, and actually all four of these are more reactive than the plain carboxylic acid. Now when I talk about reactivity, what we're trying to visualize is a nucleophile being added to the carbonyl carbon and kicking out the leaving group. So without looking at the details of these types of reactions and just making it very general, what we want to see is, or what I want to try to explain is, why is the acid chloride more susceptible to attack to give us what? To give us our substitution product plus our leaving group. So can you visualize each of these being attacked by the nucleophile and what kind of leaving group is expelled? Why don't you pause the video and do this type of analysis where we have a nucleophile come in and replace the leaving group. For each of these carboxylic acid derivatives, what I drew was a theoretical nucleophile coming in and attacking the dot. So that's a good trick. I always like to put the dot on the carbon that's being attacked and then kicking out the leaving group. So in each case we are breaking, again, this bond right here when the nucleophile attacks the dot. A couple things. Again, we're not showing the mechanism, and sometimes it takes more reagents, maybe a catalyst, to help the nucleophile attack the dot. But I'm doing this in a very general sense, and we are inspecting the type of leaving groups that are being produced when the nucleophile substitutes for this leaving group. So here I have labeled the type of carboxylic acid derivative, and here I circled the leaving group for each of these derivatives when the nucleophile replaces it or substitutes for it. Now there are two schools of thought when trying to describe why acid chlorides or acyl chlorides are the most reactive and why amides are the least reactive. The two schools of thought are listed here. Number one is probably the easier one to visualize. We want to look at the stability of the leaving groups, and the more stable the leaving group is, the more reactive the derivative is. But honestly, the better way to describe the reactivity, or to explain the reactivity, is using issue 2. Look at the electron donating capabilities of the atom neighboring the carbonyl group. So specifically I'm looking at the chlorine, oxygen, and the nitrogen. How well does it donate its electrons? Because if it donates its electrons to the carbonyl group, it will decrease the partial positive of the carbonyl, and if that's true, the nucleophile is less likely to attack. Remember that the nucleophile is partial negative, and opposites attract. Well, if we could make this carbon less partial positive, then it's less likely that the nucleophile will attack the carbonyl carbon. Let's consider the first approach, where we look at the stability of the leaving group. The more stable the leaving group, the more reactive the derivative is. So based on this trend, we would predict that the chloride is the most stable leaving group out of these four. But we need to explain that, or we should try to explain that. Well, Chlorine is a large atom, electronegative atom, so it can accommodate the negative charge. So because it's a large atom, you could think of it as it being able to spread out this negative charge over that one atom. Now that's a little bit tricky to think about because here we have the carboxylate leaving group right from the anhydride. Well, yes, this has resonance. I'm not going to draw out the result of these mechanism arrows, but, well, maybe I should. So, resonance, we'll draw it up here. You have this result. And you've learned many, many times that resonance is a stabilizing effect. But it turns out, in this case, that the large, or the size of the chlorine atom trumps that. So true, this has resonance, so oxygen is very electronegative, and this carboxylate has resonance. So it's actually quite tricky to use leaving group stability to differentiate these two, because resonance and also oxygen being actually more electronegative than chlorine would suggest that this is the better leaving group. We're going to use approach number 2 actually to differentiate between these two. So in terms of stability, maybe I should say that these are close. They're pretty equal. But take a look at our other two. That one has no resonance. So that's the loser between these two in terms of stability. And this nitrogen is less electronegative than oxygen. So now this is the loser compared to this alkoxide. So in terms of stability, or leaving group stability, definitely this carboxylate is more stable than the alkoxide, and the alkoxide is more stable than the NHR minus. It's this kind of gray area that we should use approach number 2. Approach number 2 is we look at the electron donating capabilities of the atom neighboring the carbonyl group, and if it does donate its electrons very well, then the partial positive of the carbonyl is reduced. So we are going to use approach number 2 to differentiate these two. This is the sticking point in terms of trying to figure out why the acid chloride is more reactive than the anhydride. Before I look specifically at the acid chloride, or the acyl chloride and the anhydride, let me set up the situation. We have a carbonyl group with a leaving group attached to it, and this bond is very polarized. Oxygen is partial negative. We know that the carbonyl carbon is very partial positive. It's a very strong dipole, which can attract the nucleophile, which is partial negative. So opposites attract. If we're able to, or if this partial positive charge is decreased, lessened, then the nucleophile is less likely to attack this dot right here. So I'm going to draw the two carboxylic acid derivatives, and we're going to compare which one is mitigating or decreasing this partial positive charge. Here are the two molecules I want to analyze at first, an acid chloride and the anhydride. Now let's look at the anhydride first. We actually know, or we're very familiar with resonance using oxygen. We can either resonate to the right, okay, to put the negative charge on the oxygen on the right. It's not a major contributor, but it is a contributor nonetheless. And we could also move the electrons back and get the negative charge on this oxygen up here. So is that good or bad in terms of reactivity? Especially if we're looking at, let's just choose one of the carbons, carbonyl carbons, let's choose that one. How good will a nucleophile attack that dot versus this dot? Let me finish drawing our resonance. The way I like to think about it is, without this resonance, we have a partial positive charge here. But because we can make this double bond here, because we can have donation of electrons, we are sort of quenching this plus charge. We are actually decreasing it because we're pushing electrons towards this carbon. Now yes, sometimes the resonance goes to the right, but other times the resonance goes to the left. You got to think of resonance as a hybrid structure, right? All three of these happen literally at the same time. Still, what this means is that you have this plus charge sort of decrease than if there was no electron donation, especially showing this one. If there was no electron donation, that partial positive would be larger. So this resonance actually lessens the partial positive charge. Now, it's beyond the scope of the course to explain why. You're just going to have to take it on faith. But this chlorine does not do resonance. The halogens do not make this movement of electrons to produce what? We will never see something that looks like this in terms of resonance structure. We do see that with the oxygen, though. Okay, oxygen does have the ability to do resonance like this, but chlorine does not. So what does that mean for this partial positive charge? Because chlorine does not do the same type of resonance that oxygen does, this partial positive charge is actually larger. I'm going to speculate that this resonance doesn't happen because the mismatch in size between the chlorine and the carbon, right? The size, both carbon and oxygen are in the second period, right? The sizes are comparable, and we're able to get the electrons to be shared between those two atoms much easier than shared between this huge chlorine and this tinier carbon relative to chlorine. But the bottom line is this: because there's no resonance here, that partial positive charge is unaffected, and is actually larger than the partial positive charge here. Now, thinking about that idea, can you rationalize why an ester is even less reactive? Here I've drawn the ester and its resonance, and do you see how the resonance goes towards the carbonyl to the left? There's no carbonyl on the right, so anytime this donates electrons, it's always going to the left, lessening this partial positive charge. As compared to the anhydride, where half, or not half, but a third of the resonance structures, we have electron donation to the right, to make this resonance structure here. So think about what's going on with these two electrons versus what's going on with these two electrons. These two electrons are being shared on both sides, okay? But this lone pair is being shared only to this side. So I would say that this has more electron donating capabilities towards the carbonyl than the anhydride, because the anhydride again is sharing electrons on both sides. So this has much, much greater lessening of the partial positive charge. Even more lessening of the partial positive. Okay, and for the amide, we're going to depend on the leaving group stability. This is incontrovertible. This is definitely true, that the N- is less stable than the O-. So taking those two approaches together, we come up with a reason, or the reasonings between or behind this trend in reactivity.